Hi all, let's see the next topic of Unit 2, Microprogram example. So what is a microprogram or what do you mean by the concept of microprogramming? Microprogramming is nothing but it is a process of code generation for the control memory that is called as microprogramming. Before seeing an example of a microprogram, let's first understand the hardware organization of a computer. A computer basically contains two memories. One is a main memory and other is a control memory. This is the configuration of a computer system which basically contains two memories. One is this is your main memory and this is the control memory. So a main memory is nothing but a memory or a storage location which is used to store your instructions as well as the data which is required to execute a particular instructions. And so if you see this memory here, the memory is of size 2048 into 16, which means that this particular memory is capable of storing 2048 words and each word of size 16 bits. So if you convert this into the powers of 2, it is 2 to the power of 11. So 2 to the power of 11 is nothing but 2048. So the size of the address of the main memory is 11-bit address. Okay, so the registers with respect to the main memory are the data register, address register, program counter and accumulator. We have already learnt about these registers. So address register is used to hold the address of the current instruction which is being executed by the CPU, whereas a program counter holds the address of the next instruction that has to be executed, points to the address of the next instruction. Whereas a data register is used to hold your data. Accumulator is a temporary storage location to store your information. So apart from this, we also have an arithmetic logic unit which is responsible for performing your arithmetic logic and shift operations. So whatever operations that has to be performed by an ALU, it will take, if it requires two operands, one operand should be by default it will be in accumulator, where the other operand can be stored in a data register. So arithmetic logic unit performs operations on the data which is stored in a data register and the accumulator, and once the operation is done, the instruction has been executed, the result is stored back into the accumulator before storing it back into the memory locations. So this is the so here the memory addresses is of size 11-bit address. So if you notice here, there are two ways of passing the information between the registers that are present in the computer system. Data flow between the registers. One is you can use either a common bus system or you can use a multiplexers. In this diagram, a multiplexers are implemented in order to facilitate the movement of data between the registers. So this is about the main memory. Coming to the and one more thing. So here, if you look at the data flow between the registers, in case of data register, if you look at a data register, the data register can get the information from in three ways. It can either get the information from the address register, and it can get the information from the memory, and it can get the information from the accumulator. So through these three inputs, the information can be loaded into the data register. And if you look at the address register receives the input from two ways. It can either receive the input from the program counter or it can receive the input from the data register. And coming to the program counter, it can receive the input from the address register. And then coming to the memory, it receives the input which is an address from the address register. So through our address which is present in the address register, based on the address, the particular information is searched into in the memory. So this is how the registers of the computer works. And coming to the control memory here, the control memory is of size 128 into 20, which means it is capable of storing 128 words of 20 bits each. So in the previous example, we took the memory size as 4096 into 16, but in this example, it is mentioned as 2048. It depends upon the computer. So coming to the control memory, it is of size 128 into 20, which means it is capable of storing 128 words of 20 bits each. So if it is, when you consider 128, it is in the power of 2 to the power of 8. So the address size of the control memory address size is 8-bit address. Okay. So apart from the control memory, so what is the role of a control memory in a computer? Control memory is nothing but the memory unit of a control unit. And what is being stored in the control memory? A microprogram, where a microprogram is nothing but set of micro instructions, where each micro instruction can perform one or more micro operations. So that is called as a control memory. So the control memory is capable of storing micro instructions at different addresses of your control memory. Apart from that, there is also a subroutine address register, subroutine register SBR, and control address register CAR. So these are of size 7 bits starting from 0 to 6. So if you look at the control address register, it takes the input from the address register. Here there are two memory units: main memory, which stores your instruction and data, and a control memory, which stores your microprogram. And coming to the registers, processor registers, there are four processor registers in terms of main memory. They are program counter, address register, data register, and accumulator register. And in terms of a control unit registers, there are two control unit registers with respect to the control memory: control address register and subroutine register. And the transformation of information among the registers in the configuration is done through a mux rather than a bus system. So if you look at the instruction format of a normal instruction, so it mainly contains a 16-bit format where 0 to 10 bits represents your address part, and 11 to 14 bits represents your opcode, and 1 bit represents the mode bit. So in the previous example, we have considered the address as 12 bits and opcode as 3 bits. But in this particular format, in this particular computer, the instruction format varies from a computer to computer. Here it is of a 16, the same 16-bit format, where your address part is divided into 0 to 10, whereas the opcode is divided into 11 to 14, 4-bit opcode. Here we are, instead of 3-bit, we are having a 4-bit opcode and 1 for the mode bit. So if you look at the opcode, since it is a 4-bit opcode, there are 2 to the power 4 possible operations that can be performed. 2 to the power 4 means 16 possible operations, instructions can be executed based on a 4-bit opcode starting from 0000 to 0000 to 1111. So this example will only consider first 4 possible memory instructions. Uh, we are not we are not concentrating on all the 16 memory instructions. Only the first 4 memory instructions: 0000, 0001, 0010, and 0011. We'll just look at those examples. So if you see 0000, it is a add instruction. So if you see add instruction, it performs addition operation on the contents of the accumulator and the memory location, which is specified by the effective address. EA represents the effective address. So that is done by this particular instruction. Coming to the next instruction, which is a branch instruction. So here we are going to check a branch condition if the contents of a accumulator is less than 0, which means if it is a negative, then whatever is present in the effective address, that is transferred to the program counter. Next instruction is a store instruction to store the contents of the accumulator into a memory location. So the contents of the accumulator are transferred to the memory location specified by the effective address. Next is the exchange. Exchange, as the name implies, it is used to exchange the contents of two registers. So whatever contents are there in the memory location specified by the effective address, they are transferred into the accumulator register, and whatever contents are in the accumulator register, they are transferred into the memory location. Coming to a micro instruction format, similar to how your instruction format is present for the memory, for the control memory, for the micro instructions which are being stored in the control memory, there is also a particular format called micro instruction format. So this is a micro instruction format which is divided into 4 fields. So F1, F2, F3 are considered as a single field, which we call them as a micro operations field. Whereas the second field is a condition for branching field. So the whatever condition, suppose if there is a conditional branch instruction, we have to specify the condition. That condition is mentioned in the condition field. Third is a branch field. It specifies whether it is a conditional branch or an unconditional branch. And an address field specifies the effective address. So if you look at this F1, if you look at the bits, address bit is of size 7. So when we have seen this, we have seen that it is a 20-bit format. So the instruction format is a 20-bit format. So 7 bits for address, 2 bits for branch field, 2 bits for condition field, and 3 total 9 bits for the micro operation fields. 3 bits for F1, 3 bits for F2, and 3 bits for F3. So if you look at the micro operation field, each micro operation field is of size 3 bits. When it is of size 3 bits, there are 2 to the power 3 possible operations that can be performed by this function F1. Similarly, for F2, 2 to the power of 3 possible operations can be performed. Similarly, for F3. So, this table will give you the detailed micro operations for all the 3 fields F1, F2, and F3. So if you look at all the fields, the first, so it starts from 000 to 111. So 2 to the power of 3, total 8 operations for each one. Out of this, the first operation 0000 is considered as no operation field. No operation is performed with the opcode 000. Okay. Next, coming to the other remaining fields, we have 7 micro operations performed in F1, F2, and F3. Coming to F1, and one more thing, F1 performs the arithmetic operations basically, whereas F2 performs the logical operations, and F3 performs the shift operations. So all the operations that can be performed by an arithmetic logic shift unit are performed using these 3 functions F1, F2, F3. If you look at this 001, it performs an add operation where the contents of accumulator are added to the contents of the data register and the result is stored in the accumulator. Clear accumulator. So to clear the contents of the accumulator. 011, it specifies increment accumulator. In order to increment the contents of the accumulator by 1, we use this particular micro operation. And 100, DRTAC, which means that it performs transfer of information from the data register to accumulator. So DR to AC, which means transferring of information. Between DR and AC, we use a transfer of symbol T, which means the information is transferred from DR to AC. Similarly, 101, it transfers the contents from the data register. 0 to 10 bits of the data register are transferred to the address register. You know that the data register is of size 16 bits, whereas address register is of size 12 bits. So out of 16 bits, 0 to 10 bits of the data register are transferred into the address register. So DR to AR. Next, PC to AR. So program counter to address register. It performs. Next, 111 is nothing but a write operation to perform, to write the contents of a DR data register to a memory location specified by the corresponding address specified by the address register. Write operation is performed on the memory. So that is the F1. Coming to F2, so it performs a subtraction AC minus DR and the result is stored in AC. 010 performs an OR operation on the contents of the accumulator and data register. And 011 performs an AND operation on the contents of accumulator and the data register, and the result is stored into the accumulator. And 100 performs a read operation. Here you are performing a write. So to read the contents of the memory location specified by the address stored in the address register, we use a read operation in F2 function, where the contents of the memory specified by the address register are transferred into the data register. And here AC to DR, the contents of accumulator are transferred to the data register. 110 is used to increment the contents of the data register. And to move the contents from PC to DR, we use PC. The contents of PC are moved to 0 to 10 bits of the data register. Here from the data register, 0 to 10 bits are moved to address register. Here the contents of program counter is are moved to the 0 to 10 bits of the data register. Next, coming to a function F3, the first is a no operation, and the last triple one is reserved for some specific purpose. It doesn't perform any micro operation, it is used for a special purpose. And coming to 001, it performs an XOR operation on contents of accumulator and the data register, and the result is stored in the accumulator. 010 performs a complement operation on the contents of the accumulator. 011 performs shift left on the contents of the accumulator, and 100 shift right on the contents of the accumulator, and 101 is used to increment the contents of the program counter by 1, and 110 is used to transfer the contents from the address register to program counter. So these are the specific micro operations with respect to the micro operation fields F1, F2, F3. So the micro instruction format is composed of 20 bits with 4 parts. 3 fields F1, F2, F3 specify the micro operations of 3 bits each. The CD field selects the status bit conditions, which is of 2 bits. And BR field specifies the type of branch to be used, which is of size 2 bits. And AD field contains a branch address. So target address of a particular branch. So each of the 3 micro operation fields can specify one of the 7 possibilities. So the 5 letters specify a transfer type micro operation. So DR to AC is represented as DRTAC. The condition field is a 2-bit field to specify the 4 status bit conditions. So next comes the CD, condition field. So condition field, it is a 2-bit field. So it takes 2 to the power of 2 possible values. So 00, 01, 10, 11, totally 4. So coming to 00, it is represented by a symbol U. This is used specially for an unconditional branch. So whenever this field, since it is an unconditional branch, the target instruction has to be executed next. The control has to move to the target instruction. So it is always considered as 1. Next 01. So in 01, indirect address bit. So whenever the data register, the 15th bit of the data register is set, it means that it is an indirect address. In that case, the indirect bit is set to 1. Next comes 10, the sign bit. The sign bit will be set to 1 when the contents of the accumulator, the 15th bit of the accumulator is 1. So in that case, the sign bit will be set to 1. In case of 1, 1, it means the status condition Z. Z means that, so the next field, is a condition field. So the condition field, we are going to check the status conditions. So there are 4 status conditions here called U, I, S, Z. So this U is with respect to the unconditional branch. This is always set to 1. Since it is an unconditional branch, the target instruction has to be executed next. Coming to the next bit, which is an indirect bit. So if the indirect address is specified, so this indirect bit will be set, and this will be set when the contents of the 15th bit of the data register is 1. So whenever the 15th bit of the data register is checked, if it is 1, then the indirect bit is set to 1, which means that it is an indirect address. Next is a sign bit. Sign bit will be set to 1 if the 15th bit of the accumulator is 1. So if the 15th bit of the accumulator is 1, it means it is a negative number. In that case, the sign bit will be set to 1. And finally, the 0 bit. So this status will be set to 1 if the contents of the accumulator is 0. So if there is a 0 value in the accumulator, this Z bit is set to 1. So these conditions, based on the status conditions, you can take a decision whether the particular branch will be taken or not taken. So next field is a branch field. So this is also a 2-bit field which takes 4 possible combinations: 00, 01, 10 and 11. In case of 00, the symbol is jump. So if the condition is set, so we will look at any status depending upon the status bit which is specified in the condition. So if this particular condition is satisfied, if the condition is 1, it is set, then the contents of address register is moved into the control address register. If the condition is false, if the status bit is set as false, which means simply we are going to increment the contents of the control address register by 1, that is jump. And in case of call works in case of subroutines, as we have already seen. So if the condition is met, the address register contents are moved to the control address register, and we have to, for subroutine return, we have to store the return address into a subroutine register. That is done by incrementing the contents of the control address register by 1, so that after the subroutine is executed, the control will come back to the uh, so that we can store the particular value in the subroutine register back to the control address register, so that the control will come back to the address which is stored in the control address register. And if the condition is not met, the contents of the control address register are incremented by 1. This is what we have seen in the address sequencing, jump, call and all. So return. So at the return, whatever is the contents of the subroutine register, they are transferred to the control address register to return from the subroutine. Next is the map. So this is what is we have seen the mapping technique which is used in address sequencing. The same thing is used here. So mapping is nothing but 11 to 14 bits of the data register, which is an opcode. They are transferred to 2 to 5. So mapping, the same bits are transferred. So in place of 016 of the control address register, we are giving zeros. So whatever we have seen in the mapping technique, the most significant bit 0 is given as 0. 1 and 6 bits are given as 0, where the remaining opcode as it is from the data register, it stores the instruction format. So from the instruction format, the 11 to 14 represents opcode bits that are transferred, copied same to same into the 0 to 2 to 5 bits of the control address register, where the remaining bits are set to 0. So that we are mapping the 4-bit opcode to a 7-bit address of the control memory. So these are based on the status symbols. If, based on the instruction we are giving in a branch, the particular if the condition is satisfied, it works in this way. If the condition is not satisfied, if the condition is status condition is 0 or 1, depending on that, these particular instructions will be executed.